passage of vehicles and all. Once you know what is the same thing you do and test specimen. Size is small, obviously you have to reduce the load. You have to increase the load to simulate new load. So whatever live prediction, of course, still then 20 to 30% scatter will be there. But the fact that the one which is being tested in the test can correlate with the actual structure, provided you are similarity in the knowledge. So people who have done aerodynamic wind tunnel test or CFD, they might be knowing the wind tunnel test. What do? You have to get the pressure distribution from leading edge to trailing edge or root to the tip, having a scale down model. The difference in what? Actual aircraft such a huge, but a wind tunnel you are doing the scale down with maybe 1/5 or 1/10 depending on the size of the actual aircraft. In reality, aircraft flies in the still air. In the wind tunnel, you have a model sitting fixed, but you are blowing air over the dart. But why do get how do predict that ensure that whatever you get a small type of test piece, the distribution what you get, of course you have to have a data acquisition system with the Peter tube and all to get the pressure distribution. You get exactly what are the way with a different angle of attack, side sleep, whatever you condition configuration, you get a pressure distribution that matches with actual aircraft. It happens because there the similarity is Reynolds number, which is related to the indicated equivalence airspeed and density, something like that. So they maintain the Reynolds number when aircraft flies in the air, and the Reynolds number that is simulated in the test. So that way they are able to predict the exact stress distribution at different angle of attack. Similarly here, you can, as long as if they are the same. Otherwise, if there is a changes, it is gone through a different procedure, then you have to have a knockdown factor to be applied. Now we have been studied about SN curve or smooth curve, and later on we talk about Baskin's equation. All r is equal to -1, and that can be generated based on the material properties. For the ferrous material, we saw 10⁻³ is if you have 90% of the ultimate strength, will give the top point at 10⁻³. At endurance 10⁻⁶, you have to get the 50% ultimate for the ferrous material. For aluminum, you have to go 5 into 10⁸. But what is the ratio will be different, not 50%. But even steel also there is a difference is there. This ratio is between endurance versus ultimate strength. So if the ultimate strength of ferrous metal is around 200, it varies a linear. That's a 50% comes, actually 45 degree. But if ultimate strength of ferrous metal beyond 100 KSI, more than 200 KSI, your endurance limit is fixed 100. And so that's why the 0.35 to 0.6 is go for the changes. This is a very, very generic one. So for ferrous metal is fixed, is known. And this shows for your steel, cast iron and aluminum also. It has given both SI and IS unit. And aluminum is CC, here aluminum 500, this is N, you don't say it's the endurance limit, but at 5.8 into it will be around 40% of ultimate strength. Whereas ferrous it was 50%. Again, depending on the, if it is ultimate strength of ferrous material is up to 200 only, 50%, otherwise it is 100. So once you know, you can generate, even if you don't have experimental data available to do a simple like prediction of R is equal to -1 or mean stress is 0, you just generate a smooth SN curve based on the material properties. See, that is what it's showing. To generate SN curve for smooth specimen, you need to have a ultimate strength of material, whereas 90% is the 10⁻³ because we are talking about high cycle fatigue, and this is 50% ultimate strength. But it will vary for non-ferrous. It will be 75 to 80% will be for the 10⁻³, and here it will be 40% at 5 into 10⁸. Now we'll see about factors affecting